All right. Well, it looks like everybody from the waiting room has been admitted. I want to thank everybody for taking time out of their day to join us for this month's Hot Topics in Imaging seminar. And I'm very happy to introduce our speaker this month, Dr. Brett Schulson. You may recognize him from our recent, from the speaker list of our recent symposium on AI and machine learning in imaging. He's graciously agreed to give us a return performance and dive a little bit deeper into the material that he presented last month. Dr. Schulson got his PhD in biomedical engineering from Tulane. Then he did a postdoc at Harvard Medical School and then spent 5 years as a fellow at the NIH. And before joining the team at MATLAB, he spent well more than a decade focusing on analyzing and automating the analysis of biomedical data. And now Brett is a principal engineer at MathWorks, and he focuses his time on image and vision processing, machine learning, and deep learning. And with that, thank you again, Brett, for coming to speak with us. The floor is all yours.
Oh, thank you. Great introduction, Jim. Thank you. So, hi everyone. Welcome. Welcome for those of you who saw me speak or heard me speak at the symposium. Welcome back. I'm going to go over mostly the same topics that I covered in the symposium, but I'm going to go in much more depth. This is a conversation that I typically take about 90 minutes to present, and we did it in about 20 at the previous session. This session I call From Pixels to Models, and it focuses on the fact that an image is a matrix of pixel intensity values, and with images we can do a great deal of things. Many of us have images across a lot of different fields and domains, but there's a lot of different things we can do. We can range with the capabilities from what we'll call pure image processing to computer vision to traditional machine learning and then to deep learning. And as we go through this, I'm going to talk about what I mean by those categories and how I differentiate. These are by no means definitive definitions that I'm going to put forward, but just I think some useful constructs for considering how does image processing differ from computer vision, and how does traditional machine learning differ from deep learning. Okay, so as I said, an image is nothing more than a matrix of intensity values. For those of you who are familiar with MATLAB, MATLAB stands for Matrix Laboratory. MATLAB is a very, very efficient environment for manipulating matrices. And if you're looking at that matrix, that image that's a matrix, at the element by element level, the elements of an image matrix we refer to as a pixel, and you can do a lot of intensive and very useful calculations based on those pixel-based analyses. So, for example, this is an example again that I did last time, but I'm going to go over it again in more depth. If we had an image like ricegrains.tiff that ships with the image processing toolbox, this by no means do I think that anybody is labeling rice grains, but we all have images, and we might want to do things like count objects in an image. Well, how do you do that? How do you go about counting objects? This is a very simple, very common task. And typically the way that we would approach this is we would first do maybe some pre-processing, but fundamentally we would segment the image. We call it image segmentation, the kind of the conversion from a grayscale image on the left to a binary, in this case, a binary representation of that image on the right. That process of segmentation is fundamental to image processing. And then with that binary image, we can do things like just simply count the number of blobs. I'm going to make a distinction between counting rice grains from counting blobs, because we don't really know what the blobs represent. We're just going to count clusters of white pixels. So what does that look like in MATLAB? So let's go. I'm going to spend most of my time in MATLAB today. I know that most of you don't want to spend a lot of time in PowerPoint. I don't want to spend a lot of time in PowerPoint either. So I'm gonna do this first demo. I'm going to use our live editor. The live editor is a relatively new editor in the MATLAB environment. And one of the nice things is, as I click through this, I'm going to read in this image of rice.ping. As I click through this, I'm actually incorporating the output of my processing right in line with my functionality here. So I'm going to display the image, ask how many grains of rice there are. I say the first step of counting those, as I say, is a segmentation approach. There's lots and lots of ways of segmenting images, but what I'd like to do is go up to our apps tab on the upper left of my screen up here, if you can see where I'm hovering. And if I click on that apps tab and drop down, there are a lot of different apps that extend my MATLAB session. I have, of course, all the tools that MathWorks creates. So I have a lot of, I have things that you might not have, but I believe everyone here has access to the image processing computer vision tab. And if I came down here, for example, I would find, for example, an image segmenter app, which makes a lot of sense if we want to segment our image. So I could just click on that link in the apps toolbar, or I could just call it in code. So for example, if I pass my image into my image segmenter app, I open that, and I can just interactively explore my image and try different approaches to segmentation. Now, as I say, many ways of doing segmentation. Probably the simplest way of doing this is to simply threshold the image. So these are intensity values. If I specify a threshold and say anything above that threshold is a 1 or true, anything below it is a 0 or false, that's kind of the easiest manipulation of that image. And that's what this looks like. And we can automatically select that threshold. There's a function called gray thresh that allows us to do that. That's built in. But that doesn't always give us exactly what we need. And you see that in this particular case, the image, it has a non-uniform background, and an automatically selected threshold for the top of the image might be different from than one from the bottom of the image. So we might try something like a manual threshold instead, and just tweaking. You can see how I can use these tools interactively to get a threshold or to get a segmentation. Again, because this one has a non-uniform approach, a non-uniform background, maybe we want to try something like an adaptive threshold. So in just a moment, I can play with my image in this image segmenter app. And the most useful aspect of this is that this is not a one and done thing. I don't have to do this kind of manipulation with every one of my images, particularly if I have a lot of images that are similar. I can play with it at the app level, and then I can, most importantly, I can export a function that allows me to automate that process. Okay, so I don't need that function in this case, but fundamentally, really all I'm doing is calling I am binarized with an adaptive threshold, specifying sensitivity. So I could just simply copy that line of code, or I could save this as segment image, and I have now a function that I can process many different images. So in this case, so this, as I say, is a simple I'm binarized with an adaptive threshold, and if I ran this, I'm going to get a reasonably good result from my initial segmentation. So now that I have a binary image, and remember the question we fundamentally asked was how many blobs are there? If I simply counted the blobs in this image, I've got a classic problem called over-segmentation, that all this little noise in here is going to be counted, and each one of these little blobs is going to be represented the same way that I'm going to represent a grain of rice. So what I'd like to do is do a little pre-processing or post, depending on where you are in the step, and I'm going to try and remove small objects from that image. Okay, and this again is a fundamental operation. If I don't know how to do that, I might go into my doc up here on the upper right and say, how do I remove small objects from an image? Or I like using the doc search command, allows me to do this kind of interactively. And if I launch that very quickly, I find my way to a function called BW area open. You pass in the image, and you pass in the value of the smallest size of object that you want to keep. So for example, I say I want to throw away anything that's 50 pixels or smaller. I now have very quickly cleaned up that image. Okay, so now if I count the blobs in this image, I'm going to get a reasonably good representation. Again, how do I do that? I don't know. Initially, I go to my doc, I say, how do I count objects in a binary image? And with just a few minutes of reading, I'm going to find my way to a function called BW concomp, that's connected components. Notice, by the way, here that I'm specifying 8 connectivity. This is important because this says, how am I considering the connectivity of the objects? If what 8 connectivity means is if I have a single pixel, the pixels that are connected to it are in the north, south, east, and west, and north. I think I inadvertently got muted. Can someone just verify that you can hear me?
Can hear you.
Yes, we can hear you.
Okay,
Yep, loud and clear.
Thank you. Okay, so as I say, it's important to pay attention to that little 8. If I had, for example, said BW ConComp with a connectivity of 4, if you imagine that you had a thin diagonal line with each representation along that line a single pixel, in 4 connected world, that would be maybe 100 different objects. Each pixel would be a different object. In 8 connected, that would be a single line. So you can control the way that MATLAB operates on this image. In this case, the default 8 connectivity makes sense. So I'm going to count the number of connected components, and that structure that is returned from this very quick operation tells me that there are 93 objects in that image, 93 blobs. Okay, so we're not quite done, because if I pop this out and examine it a little bit more closely, if I zoom in here, you can see that there are some of these objects, some of these blobs are contiguous, and what happens is that those objects get treated as a single object rather than multiple grains. So you might want to do something a little bit more sophisticated. One of the things that occurred to me is that the connected components matrix also gives me the pixel index list for each of those objects. I can then analyze those however I want, and I can calculate the median size of those blobs and the standard deviation. And I could, for example, create a size threshold that's the median plus or minus 1 standard deviation. So I get a size or plus 1 standard deviation. I get a size threshold of 274. The nice thing is we have additional tools in that apps toolbar, like the image region analyzer. And if I pass that image in, I can do things like sort by area. And now you can see if I click on these, somewhere between 280 and 240. In fact, our size threshold was, what do we say, 247. Somewhere in that range, I'm making that transition from single grains to double grains. And I can then do things like filter on area, and I can say, show me, for example, areas that are greater than our size threshold, 274. And now I've got an image that's just the double grains. I can then, of course, pass that image out. I can pass a function out that does that. I've already done this. And if I pass that out, I passed out a function I call find double grains. And if I open it, it's exactly the code that app just created for me. Really, it's just doing a property filter saying, show me anything larger than the minimum size. And now when I run that, if I show that, I can show the overlay of that image. And you can see that we have 4 objects that are above that threshold, and I can operate on that double grains image separately, and I can do things like add the number of double grains to the number of single grains, and we get a really good representation of the number of objects in that image. Okay. Another approach, and one that I like to highlight, is using what we call image morphology. Segmentation is one of the fundamental things we do, but image morphology is another that's going to facilitate a lot of things you want to do in image processing. Now, image morphology means we're going to operate on that image with different, what we call structuring elements, different shapes and different rules. Things like look for the maximum between the structuring element and the image, or the minimum, or things like that. This is not always trivially easy to do. So there's an example, an environment that I've shared on the file exchange called image morphology. And if I pass that image in, for example, I could say, oh, with the disk, a structuring element that's a disk, maybe I can dilate that image, and just as I change the size of that structuring element, you can see how that object changes, or I can erode it. And watch what happens when I erode it. You see at some point I've broken those connections. And if I don't care about the size, that's a very reasonable thing to do. I've just broken the connections, and now if I counted the number of grains or the number of objects in this image, I can get a much better representation of the number of grains of rice. Okay, so I'm gonna move on. I think that's a useful way of looking at our data, and I'm trying to get this out of the way. But if I pass that out, I would find my way to many different ways of approaching that problem. So you can see how, I mean, I haven't done anything looking beyond the local pixel levels. This is a pure image processing problem, and it works reasonably well. It works. If I had a problem like that, I would treat that as an image processing problem. Another kind of problem that I think is purely image processing is one that's we think of as a template matching problem. And if you had a very constrained imaging problem, like you have parts going by on a conveyor belt with a fixed camera above the objects, and the relative size of those objects is uniform, you can use template matching in a very much image processing workflow to find objects in an image. I'm going to show you what that looks like here. Okay, so in this case, I've got all this stuff that's in my way here, but let's see if I can do this. I'm going to just create an image, and in this case, I've got my search image with a stop sign in here, and I've got a template. And even though those objects look like they're very different size, I actually cropped this template image from the scene image. And if I put a disline tool on there, you can see that those are actually the same number of pixels. So this is a constrained problem. And because it's so constrained, because it works so well, I can do things like do a normalized cross correlation, wherein this template becomes kind of a search kernel. And as I move that template across my image in kind of this raster-like fashion, and just look for the match between the template and the underlying image, when I pass that template over the stop sign image in the search, I'm going to get a spike. It's going to say you found some high correlation spot, and using the location of that spot. So here we go. I've got here's the output of that correlation. There's a tall spike that says you've got something happening. In fact, the correlation is exactly 1 because it's perfectly cropped. However, if I found the location of this, I'm going to actually have several pixels that are above that threshold. So I'm going to do a little bit more processing. I'm going to just replace that broad peak with a regional max. And if I do that, I now have just a single spike indicating the location of that high match. And then all I need to do is a little bit of geometry, algebra and geometry to recognize that the location of that peak correlates to or corresponds to the location of that template in the image. And because I haven't manipulated, because I haven't looked beyond the local pixel values, this is a pure image processing workflow. The problem, though, is that whenever we get beyond that pure constraint problem, if I look at an image, for example, that is, well, make another point here real quickly. I'm just going to pause this, but the calculation that the location of that peak, I made easier for you. I called it normalized cross correlation detector. And if I run this, we'll automatically find those for you. That's a function I've shared on the MATLAB Central File Exchange. If you want that, you can go grab that. But the next point is, if I have a more unconstrained problem, like for example, my pixel, this looks like the same problem, but it's actually a very different problem. In this case, the template is a very different size than the object we're looking for. And if I did that same exact workflow, in this case, there's no strong peak in the output of that correlation space. And if I look for something that's above that threshold, I'm not going to find it. Or if, for example, the object is the same size, but it's rotated, again, I'm not going to find any matches. So how do we deal with things that are not constrained? Well, that's a nice segue into the next topic of the talk, in that if we move beyond looking at pure pixels to looking at features in the image, we make that transition to what we call computer vision. And instead of looking at just local pixels, when we start looking at the relationship between clusters of pixels, we talk about having features in the image. We can ask higher level concepts, and we can ask not only, for example, how many pixels are in this image that are above a threshold, for example. Like so here's a 3x3 matrix. If I wanted to threshold it in an image processing world, I can look at that and say there are 5 super threshold pixels. In the computer vision world, I can look at that threshold image and ask a question like, what is that? And I can interpret it as the letter L, because I'm looking beyond the local values. So in my mind, that's kind of the transition from image processing to computer vision, is when we start looking beyond, when we start considering features in the image and asking higher level interpretive questions. And with that notion, we can do all kinds of really useful things. I like to think also that computer vision is kind of a sparsification of image data. So what I mean by that is, what I mean by that is we have an image here of a bicycle, and this is a very dense representation. This could be 10 megapixels, for example. But I can very easily calculate things like a histogram of oriented gradients of that image. And you would see things like a gradient pattern that represents the front wheel, and a gradient pattern that represents the back wheel and the crossbar. That calculation is very fast in MATLAB, and it's very much lighter weight than this 10 megapixel image of the bicycle. And because it's lighter weight, we can do things much more quickly with it. And in fact, even if the front wheel were obscured or turned at an angle, there's enough histogram of oriented gradient feature information in this image or in this representation that I could say that's a bicycle, even if I'm looking at only a portion of that bicycle. Or moving further down that sparsification matrix or path, I could look at things like surf features, speeded up, robust features. Surf features are robust to things like changes in orientation and scale. So where in the normalized cross correlation failed with the stop sign detector, in this case, it would work really nicely. Now, behind the scenes, when I ask for a collection of surf features, I'm telling the computer to do to create a determinant of a Hessian matrix. If you want to know the math behind it, you can go read it about it all day long. From my perspective, all I really care about is the fact that the computer can see things in that image that are useful for classification that I don't necessarily have to see. And if I plot those surf features on this bicycle, the location of the crosshair is the location of the spike in that surf domain, and the size of the circle is the strength of that surf feature. And if I then operate on multiple bicycles across multiple bicycles and say calculate, for example, surf features, I can create what we call a bag of words or bag of features. Now, a bag of features is kind of equivalent to a word cloud. You're all familiar with word clouds, and you see kind of, here's a description of a book, and I'm looking at a beer book. The word cloud has hops and yeast and barley and malt and things like that. If I really want to characterize a book as a beer book, I don't really need to read every word of it. I just need to say, what does its word cloud look like? And is it more like a word cloud of a beer book or a word cloud of a wine book that would have a different word cloud? And that's exactly analogous to what we can do with these features. I can calculate features across multiple objects and create a dictionary definition, so to speak, of what a bicycle looks like compared to what a car looks like. And based on that dictionary definition, I can then start differentiating objects. Okay, so let's look at what that looks like. So when I go down that path of calculating features, I can do what we call a detect, extract, and match workflow. And from that detect, extract, match workflow, I can do all kinds of cool things like registering an image. So let's go do another demo. And in this demo, I'm going to read in an image of a cameraman that ships with our toolbox. I'm going to create a noisy, downsampled, rotated version of that image, and I'm going to see if I can find a correspondence that allows me to co-register those images. And of course, in your world, this might be co-registering MR data with CT data or any kind of different imaging modalities. It is actually something that's quite easy to do. So let's look what that looks like. So in this case, again, I'm going to read in an image of the cameraman.tiff. I'm going to create a noisy, resized version of that image. So I'm going to scale it by 70% or to 70%. I'm going to rotate it 30 degrees. I'm going to add noise. And I've got this kind of challenging problem. No way in heck, no, I shouldn't say that. There's no way that I can make the normalized cross correlation work in this regard. It's a very challenging thing to do. In the feature-based world, detect, extract, match. I'm going to detect surf features in both of those images and extract properties. So it's exactly 4 lines of code that I need here. I've now got features detected across both of those images, and then detect, extract, match. I'm going to match the results, and based on those matches, you're going to see something interesting. You see that there are some features that are matching well, like this elbow here matches to this elbow here. Some of these features match well, but I also have some outliers. For example, I can see that the point that's mapping to here from the edge of the coat here, that's an outlier. And what I'd like to do is to estimate a geometric transformation that allows me to map between these two images. But I'd like that modeling, that mapping, to be robust to those outliers. And again, this is something that could be very difficult, but it's actually quite easy in the MATLAB world, because when I estimate a geometric transform behind the scenes, I'm going to just open up the help on that function. Behind the scenes, you can see that that this function, estimate geometric transform, automatically implements what we call it's a version of a ransack algorithm, which means random sampling and consensus. And it's very quickly going to scan through a subset of those matched features and quickly fit a model and say which subsets of those features create a low noise model. And that happens behind the scenes without my doing anything. So I'm going to say, let's find a similarity match between this image and this image. And when I do that, I can very quickly, if you see this toggling here, I can throw away the outliers. And now that happens without any effort on my part. And now I've got a transformation matrix that allows me to cast that image forward with an IM warp command. And very quickly, I've co-registered those images despite the change in orientation, despite the noise, and despite the scale. Okay. And another point before I move on is that operation is very, very fast. It's a few lines of code. Here's all the code that I just ran through. And if I wrap that in a tick and a talk, you can actually see that happens very quickly in MATLAB. So that's 0.03 seconds it took me to co-register that image. Again, that sparsification of the information makes that a very, very efficient operation. And if I were to transform that or invert that transformation matrix, I can look at what we call the homography matrix, or the homography information, and I can recover the scale. Remember, I scaled it by 70 to 70%, and I rotated it by 30 degrees, so I can recover that information. Okay, so very useful, particularly when you have an unconstrained problem, to treat that image or the image processing problem as a computer vision problem. I'm going to move on. Before I do, really quickly, I've shared a lot of information on the file exchange. Again, if you haven't seen the file exchange, I encourage you to go take a look. There's a lot of great stuff out there. Feature-based image registration is an app I wrote, so if you pass those original and distorted images in, you can try out things like, there's the surf. You can try out different types of features. Some of them work well, some of them don't, but you can tune them and interactively find a way that to approach a kind of a custom registration problem in this case. Okay, so, and you can, of course, once you've found your results, you found your way that works, you can export and generate code in the MATLAB environment. Okay, so you see how feature-based approaches can be useful for registration. I'm going to do one more feature-based approach before we move on, because it underscores the fact that detect, extract, match workflow in the feature world is useful for quite a few things, like, for example, object detection. So in this case, remember when we had the stop sign, I was trying to find the stop sign from a template to a search image. That template would fail if my objects are at different scales or orientations or skews. Again, this is something that happens very easily in the feature-based world. So let's go back and show you how that's so similar to the other one. So here we go. Just see object detection. So I've got my scene image here is an image we call cluttered-desk.jpg. You should all have access to this image. I have a staple remover that I'm going to search for. So I have an image of a staple remover. And if I looked at this, you'd see that this staple remover in this image is at a different scale, a different orientation, a different skew than this. However, this approach using detect, extract, match works really nicely. I detect features across both of those images. I can plot the results, and you'll see again, some of those features are inliers, so here to here, and there are many that are outliers. And again, the next time I extract and match, you'll see those outliers. The next time I create my estimation of my geometric transform, those outliers are automatically discarded. And now all I need to do is calculate the position of this box that I want to transform. And then I'm going to transform the location of the box forward with the transform points forward algorithm. And very quickly, I find that the staple remover in that image. Okay. I can operate on multiple images. So if, for example, my scene is my target is my staple remover, I calculate the features in that target image or in that template image. And then I could, for example, scan across multiple images, calculating the features of each calculating the features of each. What's happening here? Oh, I skipped this. Okay, so here I load in a bunch of images from the computer vision toolbox. And if, for example, I wanted to detect which of these images has a staple remover, all I need to do is to scan through them in a for loop, calculating the features on my individual search images and find where the number of features exceeds some threshold. So here quickly I found there are two matches in that collection. One was the scene and one was the target. So hopefully you see that can be useful. Detect, extract, match. It's a very easy workflow, and it makes some things that are very difficult to do in the image processing world very easy to do in the computer vision world. Okay. So, which leads us to our next topic. When I showed that sparsification image where I said once I look at multiple images, I can create a bag of features. That what I call that word cloud analogy I made. If I'm looking at one image or one image at a time, I can just do that in a for loop. But if I wanted to, for example, take a bunch of images and characterize them as car, truck, bicycle, whatever, sports car, however you want to characterize them, that's kind of a class of operation called machine learning. And in this case, we're going to differentiate classical machine learning from deep learning, which is a subset of machine learning. And I'm going to make a couple of different points here. The first point is when I do classical machine learning, we've got a representation here of a small number of images. And I'm going to do what we call manual feature extraction. And what I mean by that is I'm going to explicitly or implicitly tell the computer what I want it to calculate from each image. Do I want to look at surf features, or do I want to look at eigenvalue features or texture? Or the point is I'm going to constrain this by telling the computer exactly what I want it to find in each of those images. And as I go through each of those images, I'm then going to create a model, and that model is going to be constrained because I'm going to say, for example, calculate surf features and create a support vector machine from those surf features. And from that support vector machine built on surf features, I can use it to differentiate car, truck, bicycle, etc. So let's see what that looks like in MATLAB. So here I've got 5 sets of objects. I've got these are all just MATLAB swag that we hand out at some of our trade shows or when we're presenting in person. A MATLAB hat, a MATLAB Rubik's Cube, a deck of cards, a screwdriver, and a flashlight. How would I create machine learning model to differentiate these? Well, it's actually reasonably straightforward to do. So let's show you what that looks like. Okay, so if you don't have the data, and I can share all this with you. By the way, you can have all the data, all the examples I'm showing you if you want to step through them more carefully or more slowly. I've got a bunch of data. The first thing I need to do, I refer to it as wrangling my data. If I had data across multiple directories, I could write my own directory command and I could parse it and I could start manually operating on a directory command. Image data store, though, makes that very, very easy. I pass in the location of my data, and I could say include subfolders as true or false, get the names of the images from the folder names, true or false. And when I do that, this image data store very quickly returns to me an object that allows me to manage all of my data. So here, for example, I have 75 images. I haven't read them all in, but I've got a full file path to all those 75 images. I've got the folder names associated with them, with each of them. I've got the names, everything I need. And I've got a method called read function that if I want to modify what happens when I read them, I can do all kinds of things like that. I can count the number of labels in each of those. And I made the point when I showed my PowerPoint slide that we're working with a small number of images. If I wanted to differentiate 5 objects or 5 classes of objects, I'm going to do this with 15 images of each class. That's a very small number of images. Certainly not what we look at when we're looking at deep learning, which we'll get to next. But with just 15 images, I could, for example, create a montage. I'm going to split my data. So I'm going to create a machine learning model. I don't want to train the model on all of my data. So in this case, I've got a method associated with that image data store called split each label. I'm going to say randomly assign 60% of my data to training, leave 40% for validation. So very quickly, I get an image data store that's just training and another image data store that's just validation. Okay. Now I said that I'm going to create a bag of words. Now, bag of words is a bag of features in the computer vision world is going to go through and by default calculate 500, a dictionary of 500 features across all of these images. And it's going to allow me to say which one of the, if I look at a particular image, what does its feature set look like? Is it most like the feature set that represents hat or Rubik's Cube or deck of cards? Now, I'm not going to do this live. It takes about, it's only 15 seconds. I could do it live, but one of the points I'm going to make is when I create this bag of features, if I open this function, I said that this is a constrained problem because I'm implicitly telling the computer when I use this bag of features by default, I'm going to say calculate surf features across all these images. So I'm constraining the problem. Okay, so that's very important, a very important notion. And I'm not doing this live, so before the session, I created that bag of features and I saved it. Now I'm just loading it. But so now I've got a bag of features with a vocabulary size of 500 and all kinds of things I can tweak, like whether my objects are upright or not. In this case, maybe upright makes sense, maybe it doesn't, but you can imagine that if you're driving down the road, upright makes sense if you're looking at cars, but if you're looking at an aerial view, there's no orientation that makes sense, so maybe you want to turn upright to false. In any event, I've got a bag of features calculated on all those images. It took about 15 seconds. I can now read in an image and look at what its histogram of words. This is the word cloud. So what does the histogram of words look like for each of those objects? Okay, and if I compared them, oops. If I compared them, I could look at you would see a different frequency histogram for each of those 5 different objects, and I can now train an image category classifier to differentiate those 5 histograms. Now, I constrain the problem by saying surf features implicitly. When I say train image category classifier, by default, I'm telling the computer to create a support vector machine based on those functions. So again, I'm constraining this problem, and in a matter of 2 seconds, I've got a category classifier, and I can now come along and I can evaluate all of my training data. Now, if I evaluate training data, that's of course telling me operate on the images that I've trained, and it's comforting to see that it's 100% accurate on the images that I train. If I look instead at the validation set, here's where the rubber hits the road. The model is actually 93% accurate. And that's pretty impressive, I think, given that I've only operated on 15 images per class. It was very easy to do. I very quickly get a reasonably accurate model. And now, of course, I've got a model. All I need to do to look at a particular image is to read it in, pass it in, and predict its membership. And for example, you can see that that's a cap. We call it a torch in Great Britain, MathWorks Cube. And I'm just randomly selecting images and showing you how that works. And this is something I just created for the most part live. Okay, so that's classical machine learning, and it's for the right problem, it's the right for the right problem, it's the right approach. You have a little bit of data. The classes are pretty distinct. It makes sense to work in the classical domain of machine learning. There are limitations though, and let's look at this. I mean, in this case, those were pretty trivial classes. In this case, for example, let's assume that I have 5 different classes of food. I've got Caesar salad, French fries, hamburgers, pizza, and sushi. And this could be different imaging modalities, and this could be cancer, not cancer. It could be all kinds of different things. I want to look at how can I create a machine learning model to differentiate these 5 classes. This becomes a much more challenging problem to make work well. So for example, machine learning. So I'm gonna start out with steering to my root folder. My root folder is where I have all my data. If I open that folder, you can see that I have, in this case, I'm gonna show you I have 1,000 images of food, of Caesar salad, and 1,000 images of French fries, 1,000 images of hamburgers, the same for pizza and sushi. Again, I'm gonna use an image data store to wrangle my data very quickly. I can very quickly count the number of labels, and you see I have 1,000 of each. And in this case, those images are relatively large. And another distinction I want to make between classical machine learning and deep learning is that when I create a classical machine learning model, by and large, I need to have all of my data available to my computer at the same time. And this is very limiting. I can't possibly send 5,000 large images to my computer memory. Way too much. Even though I have 16 gigabytes of RAM, this is going to overwhelm my computer. So this time, when I select my data, I'm going to split my data into training and validation. This time, I'm going to say just assign 10% to training and 10% to validation. And I'm going to, roughly speaking, I'm going to just discard 80% of my data to make the point I'm making here. So very quickly, I've got 100 training images of each class and 100 validation images of each class. Again, I'm going to create my bag of features. And again, now I can look at the differences in those histograms for those 5 classes. And again, I create an image category classifier. And by the way, this time, if I had done this live, that would have taken about 13 minutes. Certainly don't want to watch that happen. And then training the classifier takes about 80 seconds, just almost about a minute and a half. So I'm just doing this with pre-calculated data. And more importantly, I'm going to look at this and say, with 100 images in each class, this really doesn't look very impressive. I say that's pizza, it's really sushi. That one works. That one works. That was okay. This doesn't work well. That's pizza. It says it's French fries. That one didn't work. So the next question we can ask is, well, it looks like it's working sometime. It's not working all the time. How do we really validate that? How do we say how good it is? The way that we do this typically is by computing what we call a confusion matrix operating on our validation data. Now, what I'm gonna do here is I'm gonna scan through my validation data set, I'm going to do this in parallel. So I've got a parallel pool running. You can see this on the bottom left of my screen. I've got 3 workers running in the background. And when I run this, I'm going to scan through and I'm going to create this visualization of the accuracy of the model. And on the left, you see the true class. On the bottom, you see the predicted class. Everything on that main diagonal in this confusion matrix is accurate. This is a Caesar salad predicted to be Caesar salad, French fries predicted to be French fries. Everything off of that main diagonal is an error. And if we look at if we sum the number of images on that main diagonal divided by the total number of images, we get an overall accuracy of 54%, 55%. Not particularly good, even though I operated on 100 images at a time. So I've constrained it. I've said use surf features and a support vector machine, a linear support vector machine. How do I improve this? If I've got 50, we'll say for our purposes, 55% isn't nearly good enough. How do I improve it? Well, what I would like to do is to remove some of those constraints. And the way that I'm going to do this, I'm going to say, all right, we calculated surf features, but instead of just saying, let's create a support vector machine, let's remove that constraint and let's look at the classification learner app. This is an app that ships with the statistics and machine learning toolbox. I'm going to cast my data to a table. I'm going to open up the classification learner app, and I'm going to start a new. I'm going to look for a new model that makes gives us a better result. So let's say we start a new session. I'm going to select that table I just created, my 5 class data. Notice that I can do cross-validation or holdout validation or no validation if I want. I'm just going to do this by default. But by default, I'm going to go through and I have 500 different features calculated, and the 501st row is going to be my class value output. So let me just start a session. And this time, instead of just saying, let's create a linear support vector machine, which is down here, I can create decision trees or discriminant analyses or naive Bayes classifiers or different flavors of support vector machines, et cetera, et cetera. And if I don't know what to do, I could say, let's train them all. And I can train them all in parallel. I've got my parallel pool open. I say train. And very quickly, MATLAB's going to go through and start telling me what is the accuracy of each of these models and how can I get above that 54%. And you can see here, for example, the linear model got a 58% here. The quadratic support vector machine gets me up to 60%. For each of these models, and I know 60% isn't very good, which is another point I'm going to make, but for each of these models, I can see how accurate it is, what is the prediction speed, what is the training speed. I can look at things like the confusion matrix for each of those models or the ROC curve. When I like what I see, which is typically going to be the one that gives me the highest accuracy, but not necessarily. You could look at you could decide based on confusion matrices and other properties. But when I like the one like for example this quadratic support vector machine, I can generate a function that allows me to do this the next time without opening that app environment. So I just pass in my training data, and it's going to pass out that model for me. Okay, so in this case, I've got a quadratic support vector machine. I pass it up. Whoops. Let's load this. Didn't pass it out. So I'm going to load it. Sorry, question?
No, nada, no me ha regresado.
Okay. So I'm going to load in, this time, a cubic support vector machine model. So I've removed the constraint saying it's just a pure linear support vector machine. Turns out that the most accurate model it found was a cubic support vector machine. So I load that in, and let's now try that on our test validation data again. And now we went from 54% to 55.2%. Not particularly good, right? So just looking at the individual models, the individual operations don't look so good. The next question is, how do I improve that? And lots of things I can do. If for example, look at the confusion matrix, I might notice that a lot of hamburgers or a lot of sushi is miscalculated as hamburger. A lot of hamburgers are miscalculated as sushi. So for example, I could create another model that differentiates in the case of sushi or hamburger that looks at kind of a finer grained resolution of those two classes. So I create a two-class classifier. This time when I pass in my 1,000 images, I can pass in a lot more images, and I can create a two-class model and hopefully get to a much more accurate representation. So now when I look at sushi versus hamburger, I get to 74%. And I can start doing things like creating a composite representation of, let's look at 5 classes, and if it's sushi or hamburger, let's create a two-class model and make a composite calculation. And ultimately, I'm not going to belabor this point, but ultimately when I get to this, I go from 54% with a linear support vector machine, 55% to cubic, 59% if we create that ensemble. And we're really even struggling. We're not getting anywhere we need to be with that, the accuracy of a classical machine learning model. And the reason is, even if I add in a lot more data, the complexity of the problem gets much bigger. The computational cost gets much bigger. It takes a lot longer to train. And even with a lot more data, I was only ever able to get that ensemble classifier up to about 64%. And for most of our purposes, we're going to say that's not good enough. And what do we do next? And that's a very good introduction to the next topic, which is machine learning versus deep learning. So I took pains to make sure we differentiated, and when we represented that machine learning is a constrained problem, classical machine learning, and I constrained it by saying support vector machine and surf features. And it's very possible that surf features are never going to find what you need to find. I can give it 1 million more images, and it's never going to find surf features in those images that are going to give a good differentiation, which is very different from the way that deep learning works. In deep learning, we have a relatively unconstrained problem. So I'm going to take a lot of data, represented here is a lot of data. I'm going to specify just the computer architecture of our neural network. And I'll tell you what I mean about architecture in just a second. And we're going to let the computer figure out what it needs to know. And because it's unconstrained, it does an amazingly good job at a very complex task. So what you're seeing here is a video of AlexNet. It's a famous neural network. It's trained on 1,000 classes. There were 1,000 images per class. So we're talking about training on 1 million images. Imagine how much fun it was to train this. The training actually took something like 5 or 6 days the first time it worked. But once you've got the trained model, the inference with that model is very fast. You'd be seeing this live, and it works amazingly well. And it works so well, in fact, that it allows us to drive down the road in our Teslas with our hands off the wheel and let the computer just visually inspect the world, implementing these computer vision models, these deep learning models, sorry, behind the scenes, and making inferences in real time that are really, really good. So to differentiate between classical machine learning and deep learning, we're going to say deep learning operates directly on the data. In this case, we're talking about images, but we could be talking about signals or text or natural language. It could be anything. We're going to do what we call end-to-end learning, which is throw the data at an architecture and let it just churn away until it figures out the ideal classification, the ideal path through those data to classify and differentiate. And because we're not constraining the model, where the traditional machine learning saturates, the deep learning architecture is not going to saturate. It's going to scale with the data. So if I give it 1 million images and it gives me to 99% accuracy, if I give it a million more, we might get to 99.9% accuracy. And the more data we give it, and the more false positives we correct and false negatives that we correct, the better the model is going to train until it ultimately gets to as accurate as we need it to be. Okay, so very important distinction. It's a distinction that's fundamentally changing the way that we work in the world, for medical diagnostics, for driving, for speech processing. Essentially everything that we do is being changed by deep learning. So when we talk about deep learning, we talk about the depth of the model being the number of layers in the architecture. You can think about the layers as being kind of like building blocks, functional building blocks, and you can stack them in a long linear pattern, or you can stack them non-linearly, but you're going to pass your data in, and it's going to pass the information back and forth between these functions, and you can reorder them, and you can change which functions are in those blocks, and fundamentally you get an output that's a classification or a detection or a regression. Okay, when we're looking at images, we're often talking about convolutional neural networks, or CNNs. You probably have heard that term. I'm not going to talk about all the layers that go into a convolutional neural network, but I'm going to talk about a few that are very, very common. And why is it a convolutional layer? Okay, so when we look at images, you'll very often see in the deep learning model, you'll see a convolution layer or multiple convolution layers, max pooling, and ReLU. In fact, you'll see these repeated as little triads, or maybe it'll be a normalization in there with it, convolution, ReLU, pooling, convolution, ReLU, pooling, over and over again. And at the end, we're going to get our result. So why convolution? Remember when we looked at the stop sign and we did the normalized cross correlation, and we said that if you have a pattern that you're looking for at the right scale, that pattern is very good, or the cross correlation, the convolution is very good at finding those patterns. So if, for example, I wanted to create a model that differentiated between the digital digits from 0 to 9, the patterns in that 0 represented here on the right would be very different from the patterns that we would see in a 1, right? So these patterns on the right are our convolutional kernels, the equivalent to the template of the stop sign that we started with. The difference is I didn't tell the computer, I'm not going to tell the computer, these are our patterns for a 0. Instead, I'm going to say, here are enough 0s and here are enough 1s. Go through those data and automatically figure out what the right convolutional patterns are, okay? And then once I've done that, I'm going to pass it through into a pooling stage. Pooling, it just allows me to shrink the images and look at different scales. So for example, 2x2 pooling is going to replace that 2x2 block with the maximum value. And it's going to let me look at things at different scales. So it becomes scale invariant. And rectified linear units, or ReLU, is simply going to add nonlinearity by saying anything that's a negative set to 0. And that nonlinearity is very inexpensive to implement, but very important in making this work well. Okay, and at the end, you're going to see a fully connected layer that takes all the output from the layers above it and creates a vector that kind of lets you get the relative score for each category, a softmax layer that's going to turn those scores into probabilities, and then finally a classification layer that maps those softmax probabilities back to the input classes and lets us classify. So all that said, I'm going to give you an example of how this works, and I'm going to show you that there are actually two fundamental ways that we typically approach this. The first is kind of the gold standard. You want to create a model that's going to differentiate between cancerous tissue and non-cancerous tissue, or car, truck, bicycle, for example. If you had 1 million images of each of those classes, you could start from scratch and you create this gold standard model that's going to work really, really well at the end. Most of us don't have 1 million ground truth images of cancer and non-cancer, or bicycle and non-bicycle, or bicycle truck. So doing this from scratch is not always practical. And in fact, the way that most people are doing deep learning these days is by doing what we call transfer learning. We're going to take a model that's already been trained, and we could take, for example, the AlexNet model that you saw the video of, and I can say, as this model was trained on 1 million images, it became a very good feature detector. It found color feature and texture feature and everything it needed to know to differentiate those 1,000 classes. I can repurpose what it learned from those 1,000 classes to do a different task, to differentiate dogs from cats, for example. And in doing that, I'm leveraging work that's already been done by other researchers, other deep learning experts to solve my problem. And I can do that with a lot less data than I need if I'm starting from scratch. The way that we typically do that, we load in our pre-trained network. We're going to replace a few layers. I'll show you what that looks like in just a second. So we might replace the softmax layer, the classification layer, and then we're going to retrain with a small number of new data. And we're going to say reclassify the data to our new classes. And doing that, let's go back to our food network here, our food classification. Remember, we looked at 5 classes of food in a classical machine learning architecture, and fundamentally, after a great deal of effort, we were able to get up to 64%. And it's not particularly exciting, not particularly good, but in a deep learning workflow, this looks a lot better. So let's go do this in a deep learning workflow and show you what it looks like. Okay, so and this, by the way, is my last demo, and then we'll wrap up and we'll open it up to questions. Okay, so I said I'm going to do this in a transfer learning workflow. I'm gonna load up my data, and I'm not going to train this live, even though it's transfer learning. It doesn't require as much data as if I were starting from scratch. I'm not going to train it live. I'll show you what it looks like. No, but I am going to start with a pre-trained network. In this case, I'm going to start with AlexNet. Loading AlexNet into MATLAB is as easy as saying net equals AlexNet. I load that in. I've got everything that AlexNet was trained on in those million images. I've got the architecture, and I can look at the architecture by analyzing the network. The architecture of AlexNet is a very linear model. I've got my input layer at the top. So this is my image input layer, 227 by 227 by 3. Those are the size of the input layers, input images. And in this case, that's a constraint. That means that any image I want to look at with this model, I have to cast to 227 by 227 by 3. But then you'll see convolution, ReLU, pooling, convolution, ReLU, pooling. In this case, there's some normalizations as well. And then finally, at the end, fully connected probability and the classification output layer at the end. Okay, so there's my architecture. And oops, let's see here. There's my architecture. And if I wanted to look at the last layer, the classification layer, layers of end, I can see what layers, what classes was that model trained on. There's the 1,000 classes of AlexNet. And if I wanted to differentiate between spaghetti squash and a spider monkey, this model is going to do a really good job for me. So let's load in an image called peppers.ping that ships with our tools. And I'm going to classify it, net.classify, resizing it to our target size. And the model's going to tell me very quickly that that's a bell pepper. So let's look at this for a second. I've got a bunch of different vegetables in here. I've got garlic and I've got onion. I've got some bell peppers. And it's going to look at this and tell me it's a bell pepper because the model happens to have images of bell peppers. It has a class of object called bell pepper. If it also had onion and garlic, it's still going to tell me it's one of those objects. This is a detection. This is a classification network. It's going to tell me it's bell pepper or garlic or onion, and it's going to give me a confidence metric associated with each of those classes. So interpret carefully, but know also that if you look at an image that it has never seen before, so this model has never seen French fries. If I ask that model what does it think it is, it's going to tell me it's carbonara. And if I look at the output, the classes that it's most commonly or most likely to be, it's things 59% says it thinks it's carbonara. It might be pretzel, it might be chocolate sauce. So typically, when you're using these classification networks to characterize your image, you don't want to just look at the first output. You want to be careful. I've seen models that give you 100% accuracy, 100% confidence, and they're 100% wrong. I've also seen 10% confidence and they're 100% right. So interpret carefully. Look at the top 5 classes, make a decision about how confident you are, and then proceed. But let's take these data. Again, I'm going to read in my data with an image data store, steering to my image path. And so I've got my images. Okay, I'm just looking at each of those 5 classes and saying, what does the model currently think these are? So French fries, it thinks it's carbonara. Sushi, it thinks it's a hot dog. Pizza, it thinks it's a wok. So clearly, we don't have the right classes to detect these images the way we want to detect. So this time, when I split my data, I'm going to randomly assign 70% to training, 20% to testing, and this time I'm going to include validation data. I'll show you why I do that in a minute. Okay, and now I'm going to reclassify, repurpose my 1,000 class classifier into a 5-class classifier by simply replacing the fully connected layer with a 5-class fully connected layer and replacing that classification layer and retraining. And the reason I'm doing this, the net in this case is AlexNet, but you can start with any different model like the VGG models or GooglyNet, which is a DAG network. For any of the series networks like AlexNet, that's just a long straight path of functions. This is kind of the easy way of doing this. But if you have a kind of a less linear model like a DAG, we call it DAG network, the approach is slightly different. So you would want to remove the layers with a function and then add in layers with a function. But beyond that, the approach is the same. So I'm just going to replace my layers. I'm going to specify my training options, and these are just by default. Stochastic gradient descent, these are just default training options. And I'm going to say train my network. And I'm not going to do this live again, but what I'm going to show you instead is a video. Let me see if I can get this to bigger here. It's behind my, yep. So it's behind my presentation mode panel. But what you would see here is you see a 5-class model. On the top, you can see the accuracy of that model as it iterates over time. And then on the bottom, the loss function. This is the loss. You can think of this as an optimization problem. We'd like to see the loss go to 0. We'd like to see the accuracy go to 100%. Instead, in this case, I've got a 5-class model, and the accuracy is hovering around 20%, which means it's essentially useless. And the black dots here are the validation data. So as we pass these images in, we're saying train the model, and every in this case 50 iterations, also test the model on our validation data. So if, for example, you saw the accuracy go to 100% and the validation staying around 20%, you can decide, you can stop the modeling and say, I'm probably overfitting. My model's not really working well. Okay, so why am I showing you a 20% accurate model on 5 classes? Well, because when you go back to your workspace and you try this, it's very likely that when you try these default properties, it's going to fail. Default is really hard to do, especially in deep learning. So the next thing I'm going to do is I'm going to say, how do we take those defaults out of the picture? And the way that we're going to do this is, well, if I classify this, you're going to see that that's a 20% accurate model. But the way that I do that is to do what we call we're Bayesian hyperparameter tuning. The inputs, what we call are hyperparameters. These models are very sensitive to those inputs. And if I run this, it's fundamentally going to tell me that your best approach to solving this problem is not going to be using default properties. And I know I can't make this much bigger, but in just a moment, it's going to tell me that rather than using your default initial learning rate of 10 to the minus 4, maybe a better starting point is 10 to the minus 3. And I just did that automatically. So I'm going to come back and I'm going to change my initial learning rate, particularly very sensitive to initial learning rate. I'm going to change it to 10 to the minus 3, and I'm going to retrain. And now my accuracy is going to start trending toward 100%. The validation are keeping up with the accuracy. The loss function is going to 0. That all looks good. So I'm very confident that I now have a much more accurate model in the works. So I'm going to let this train for just a moment, and now test it on my data. And remember, we had an accuracy of 20% here. Now retrained with a different initial learning rate. I think I'm busy here for a second. But now we've got the accuracy up to 90%. And remember, we churned away for, you didn't see me churn away, but I churned away for hours in the classical machine learning workflow, and I got up to 64%. With just a few minutes of deep learning, we're at 90%. And now it starts looking really good. I can look at an individual image. Pizza looks like pizza. French fries look like French fries. So it looks like we've done a much better job here. Okay, couple of quick final topics. If 90% is good and you're done, and if you're happy with that, you can stop. For the most part, we want to take advantage of that, the notion that these deep learning models don't saturate. We want to eke out as much information from these data as we can. One way we can do that is to augment our data. I could say, when I look at this image to train on it, maybe if I flip it left to right, or randomly crop it, or randomly scale it, I can get more information out. So I can create an image data augmenter object, and I can retrain on that augmented data. And in just a few minutes, we get, even without adding any more data to our model, we go from 90% to 92%. Okay, and 92 with again no additional effort, just a little bit more computational expense. We get up to 92%, and if you're happy with that, you can stop. And if you're not happy, you can ask, how do I improve this? And the fundamental way to improve it is to add more training data. These aren't going to saturate. The more training data I give it, the better the model is going to get over time. Or in this case, I did a transfer learning based on AlexNet, which is a very simple model. Maybe I want to start with more complex architectures like a DAG network, like GooglyNet, and let it solve a more challenging problem. Okay, so hopefully that kind of gives you the distinction between these 5 classes, between image processing, computer vision, machine learning, and deep learning. Fundamentally, when you get into the deep learning realm, you're going to have to ground truth a lot of data. You're going to have to label a lot of data to tell the computer what you want it to learn. I'm just going to close up by saying we have some really good labeling environments, like an image labeler and a video labeler and an audio labeler and a signal labeler. If you have big images, like large pathology images that are too big to fit in memory, we can help you with those with custom environments as well. So we can't take all the pain out of ground truthing, but we can take as much of it out as possible. These are all extensible. You can automate within these environments, and very happy to have separate conversations with you about that. Everything we've done so far has been a classification or bounding an object in an image kind of problem. I'll show you that we can also do things like localization, pixel level classification, what we call semantic segmentation. We can do deep learning on text, natural speech, data, et cetera, et cetera. Okay. Once you've got your models generated, you might not want them running on your local hardware, your local computer. You might want to export them. We have tools that automatically generate code for deployment to Intel architectures or NVIDIA CUDA processor, NVIDIA GPUs or ARM processors. We're certainly happy to talk to you about auto-generating that code as well. I'm just going to finish up by saying that Gartner is an independent research company that looks at different companies and different domains. If you look at here in this Gartner Magic Quadrant on ability to execute versus completeness of vision, you'll see that MathWorks is considered a leader in deep learning for our overall capacity to execute on deep learning, even way above Anaconda, Python-based approaches. So fundamentally, we can handle the entire workflow from data in, pre-processing, ground truthing, model generation, to deployment. Happy to talk to you about any of those. I'm going to just finalize by saying Angelo D'Amato is also watching. And Angelo, I think for most of you, he's the account representative. If you have questions about how you can access data or access tools or license tools in MATLAB, he's the person. Here's his contact information. I'll share that with you. And even if you have technical questions, ping him and he'll get you in touch with the right people. And with that, I'm going to say thank you. I hope that was interesting and useful, and let's open up to questions.
That was fantastic. Thank you very much for the presentation. You covered an incredible amount of material. Let me kick off so you had started to say somewhere in there, if we want to be able to step through that demo that you were just showing a little bit more slowly. A lot of us, the vocabulary, it takes us a little bit longer to process the things that you're saying. So are you posting that? Is that demo posted somewhere that we can step through a little bit more slowly? And
it's not posted anywhere, but I'm very happy to share a link. It's a non-expiring link, and I'll give you an access code that you can get it. You can download everything, and you can start stepping through it at your own pace, and including the PowerPoint. Everything is in there.
Oh, fantastic! So is this something that people will contact you to get, or Angelo, or?
I will. I don't know. I'm not. I can't see who's talking. Is that Jim?
Oh yeah, sorry.
Yeah.
Yes,
no,
yes,
that's right.
me.
Jim, I can send the link to you or to Don or to whomever you want, and you can share it or however you want to distribute it. Just let us know. It's a static link, so I'll.
Okay, well, if you don't, in the interest of time and not having this discussion for too long in front of everybody, well, why don't you go ahead and send it to me, and then I can send it out to anybody that's interested. So we also had a number, very quickly before we move on to the questions that the number of questions that people have entered in the chat box. In terms of licenses, we can run through the demo without specific licenses for computer vision and deep learning, or do we need to have those licenses on hand? Looks
again, like someone muted me again.
Yeah.
Actually, that's a question for Angelo. I don't know what your current license model is. I think that you all have the tools that I talked about. If not, we can certainly set you up with them. You do need MATLAB and 5 tools to run through what I did. So you need MATLAB, image processing, computer vision, statistics and machine learning, parallel computing, and deep learning. And with those 5 tools, you can do everything that I did. If you don't have any of those, ping Angelo and he can set you up.
Okay, very good. I lost my chat window. Let's see, where did the chat window go? Oh, there it is. Okay, so the first question from Jack Verusco. A lot of these tools are used for analyzing single slices. What is the, how complex is it to ramp up to 3D analyses?
A little complex, but certainly doable. So it's a great question, and we've actually spent a lot of the past year, two releases, maybe a year and a half of ramping up from transitioning from pure 2D to 3D. We weren't always pure 2D, but we've got a lot more capacity to do 3D imaging. There's a really nice demo in the doc for segmenting lung tissue, and I think there's one of brain tissue as well, from MRI data, just looking at a 3D stack. And of course, ground truthing is more challenging. You might have to ground truth in 3D, but we have the tools in place, and we're continuing to extend our capabilities. In fact, one point I want to make is that if you're doing core image processing, you could probably work with a version of image processing toolbox that's 5 years old and not feel the pain. But if you're doing deep learning, you really need to stay current with our tools, because we've got a lot of development efforts focused on these fields. Every release we create, every release we put out, we've got new functionality. So with the current version, right, we're beta testing 2021A. Even that represents a step above 2020B. So stay current, and you'll see that there's a lot of new functionality for 3D. And Jack, if you want to have a separate conversation, I'm very pleased to do that offline.
Next, Rosanna Terrasciano. I'm sorry if I just slaughtered your name in front of everybody. Very interesting overview. Do you have any suggestions or comments about the use of MATLAB for quantitative MRI analysis?
Yeah, that's a great question. It's a challenging question to answer kind of on the fly. Again, Rosanna, I'm very happy to have a separate conversation with you about that. And we can dig in, and I'm happy to look at it because I'm not an MRI expert by any means, and I'm not sure what the relaxation parameter really looks like. I think that, for example, if you wanted to do deep learning, you would replace the classification network with a regression network, and you would regress the data to a relaxation parameter. So the approach is very similar, but like in the deep learning regard, the network would look different. So it's just a matter of understanding what you want out of the network and selecting the right network or the right layers in that network to make it give you what you want.
So I guess one of the big challenges with that would be having the ground truth to train the network, right?
Always.
That's always a little bit fuzzy when it comes to quantitative imaging.
Absolutely.
One of our attendees said, "Great presentation. Do you have any practice workflows using AlexNet that we can go through in a tutorial?"
So that's a great comment. That's my favorite comment so far. No, so yes, AlexNet is. I don't know if you don't know what AlexNet is. AlexNet was that model that we looked at that's trained on 1,000 classes, 1,000 images per class. It's really the model that started the revolution in deep learning. You can load in AlexNet with that one line of command, and if you search for AlexNet in our doc, you find many examples that are built on AlexNet in this transfer learning regard. So just the first time you use it, you'll say net equals AlexNet, and you say you don't have AlexNet, and you'll click on a link, and it'll automatically load it up for you. So it's an external package. You just accept the licensing, and you're good to go. And there's lots of demos that are built on it.
Oh, fantastic. One user, one of our attendees said, "What tools should I use to map surface curvature, such as CT or MRI image data?"
So my guess is when I launched in the stats and machine learning world, I use the classification learner app. But there's in the curve fitting world, there's a tool called Curve Fit. It used to be called Surface Fit, but I think we just got rid of the surface because it works with 2D and 3D. But you could pass in your X, Y, and Z data and just interactively try out different approaches to fitting a surface, for example. And you can specify types of fit. You can specify is an exponential or a polynomial fit or an interpolant fit. So you just play with it, and then you can generate the code to do that. I think that's what you're getting
at. There's a question on here, and this is one that I was thinking as well. Moving beyond two-dimensional data to three-dimensional data. What about higher dimensions? Are there tools that we can still work in that space, or are we kind of waiting? Will we have to have a future release of MATLAB that would support that dimensionality?
So I can't answer that in general because every problem is a little bit different. What I would say is MATLAB stands for Matrix Laboratory, and MATLAB will deal very well with n-dimensional matrices. And it's fundamentally what we've been doing for 30 plus years that we've been in business. But depending what you want to do with those n-dimensional data, like for example, creating deep learning models from n-dimensional data, it's challenging for many regards, for many reasons. Like for example, how do you ground truth for an n-dimensional data? So those are things that we're still trying to figure out. And if you have any problems that you want to see solved, we're at the cutting edge here, building models on n-dimensional data. We're very happy to have your input and understand how we can build new tools to support this kind of stuff.
Well, I can think just off the top of my head, spectroscopic imaging on MRI, three-dimensional, so 3 spatial dimensions, and then a spectral dimension on top of that.
So
comes
that's
to my mind.
4 dimensions.
Yeah.
So, but that's probably that's like 4 dimensions with the fourth one being time. That's probably still manageable. But what if there's 5 dimensions? There's spectral plus time, and then it gets unwieldy fast.
Yeah, we have that too, but that's, I'll go from 2 to 3 to 4 before we try to tackle 5.
Right, and that's exactly where we are, and that's exactly where the world is trying to understand how to build models. Now, all this stuff is relatively new. I mean, 10 years ago, no one had heard of deep learning, really.
Yep. And it seems even I'm a total novice on this, but it seems that this is a really fast moving field.
Huge. Yep.
Patrick Ford also asked, is there a good index of available tools? Notice some of the tools you used have written for himself and could have saved a great deal of time and effort.
I'll tell a story. When I was writing my dissertation 25 years ago, I was quantifying retinal blood flow, and I needed to measure the diameter of vessels. And I just I was in New Orleans. I took a walk on the levee, and I thought, if I did a derivative across a profile, I could find the edges of the vessels. And I wrote this function that worked really nicely. And then I realized that there's a function called edge that did exactly what I did. So best thing is first, search the doc. So very often there's functionality in the doc. Second, there's a lot of tools on the file exchange. If you haven't tried the file exchange, there's a collection of hundreds of thousands, maybe even millions at this point of user contributed functionality that allows you to do a lot of things. And things, a lot of people, like math workers like myself, have contributed a lot of tools. So first, look in the doc, do a Google search, do a search of the file exchange. And if you can't find it, if you think it's something that someone else might have tried, might have solved, ping Angelo, and he'll ping me, and we'll see if we can hook you up with something. But just a little bit of searching can save you a lot of effort. I understand what you're getting at.
Well, this has been just fantastic. Are there any more questions from the audience?
I see there's a question about UNet. Yep,
Oh,
UNet
yeah.
is supported too. So just do a doc search for UNet, Googling Net, all kinds of different networks. Yep.
All right. Well, fantastic. Brett, thank you so much again for spending another hour and a half with us and sharing some of your hard-earned wisdom. We really appreciate it. I think it's been a fantastic presentation, and I hope that we hear more from you again in the not too distant future.
Call us whenever you want us to talk. I'm happy to talk, and it was a pleasure. Thank you guys for listening.
Thank you very much. I'm sure you can hear the raucous applause in the virtual background.
I hear it in my head.
Yeah.
Yes.
Great.
Okay.
All right. Thank you so much.
All right. You're welcome. Bye-bye.
Bye-bye.